now let's consider another example. This one is called neutral type delay differential equation. And this one is different from the previous one, since we will find that we have the derivative of x here at time t, and we also have derivative of x at time t minus 2. So we have two derivatives here, but they have a different time. And for this kind of system, we cannot use the 2, 3, because for this kind of system, for this function, there should only be a term like this. It does not allow you to have a delayed derivative term in this function. So the DDE25 function cannot be used directly. So how can we solve this kind of delay differential equation, a neutral type delay differential equation? Again, we have to define the signal x here. Here x is a vector. And once we have defined the x, then if we introduce the integrator, we will have x dot at time t. So we will see that this block can be used for scalar signals as well as vector signals. So this is the signal of x. And this is the input signal u. We can have for instance, we can have a signal source. For instance, there is a set function there to describe the u signal. And u signal should be multiplied by a gain, matrix gain B. And how about this one? Since we have already defined the signal x at time t, then if we use a delay term with a delay constant of tau 1, then we will have this signal like x t minus tau 1. And we can multiply this signal by A1 matrix to define the first term on the right-hand side. And now let's check the other signal. A2 times x dot t minus tau 2. We can get the signal here. And then place a delay at time tau 2. So this signal will be x dot t minus tau 2. And we can also multiply it by A2 matrix. And now we have to add these three signals together. Then we can create a simulation system for the delayed differential equation. We can then make a code. Yeah. So for this kind of system, we cannot easily solve with the Matlab command, the DDE25, because it cannot handle neutral type delay differential equation. What we can do only is to create a simulating block diagram. So the name of the block is C7-IMDB3, which is exactly the same as the one we defined as h. And this one is xt at time t, and this one is x dot. So we have to introduce delay here and here. And then we can compose a block diagram like this. And before that, we have to define the variables A1, A2, and B for Matlab workspace, and then perform simulation. And in the system, we have only one output. So what we need to do is to use a command, plot command, to draw the final result, the step response of the system. And you can see that in the system, the signal X is a vector which is composed of 3 components. So as a result, we will have 3 curves like this. And how can we validate it? What we need to do is to change the parameters here in this dialog box. We change it to 10 to the power of minus 10. Then we can perform simulation again, and we can hold the original result and draw the new result again on top of the old results. And we may see that the result of the 2 cases are nearly the same. So we say that the results are acceptable. If you are not happy with the result here, you have to further reduce the boundaries, the relative error tolerance to even smaller numbers, 15 or even smaller numbers. But virtually we will say that these results are acceptable, so we say that they are correct. So this is a very brief introduction on differential equation solutions. Now let's consider how can we solve control systems, control system problems. For instance, how can we simulate multivariable control systems? And how can we process computer control systems where the controller is a discrete type system, where the plan model may be a continuous type system? And how can we handle time-varying control systems? And these topics are quite difficult to be solved with the use of Matlab commands. However, with the use of simulink, it might be easier to solve. Now let's consider the multivariable control systems like this. Suppose the plan model is given like this, and there is a pre-compensator, a matrix like this. How can we solve this kind of problem? Open loop, step response, how can we solve that? For linear systems, we know that in Matlab we can describe the plan model with an LTI block, which is a linear time invariant block. For instance, we can use TN command with delay to model this part and this part, the 4 sub-blocks. And then we can use a command like this to define the matrix, the transfer function matrix. And once we have defined it, we can easily perform simulation on this kind of system. However, if the system is preceded by a matrix here, KP, then we cannot multiply them together like this, because there is delay terms on different transfer functions, sub-transfer functions, and delay constants are not the same. So we cannot use this kind of multiplication to get the overall model. So we cannot use LTI blocks, LTI objects to solve this kind of problem. So now what we need to do is to construct a simulink block diagram for the system. And for this kind of system, what we need to do is to draw a block diagram like this. It seems to be rather complicated to handle it in this way, but I think it is the only way to model it. This is the